Hi everyone, so this is the first of a few videos, maybe 3 or 4 videos that I'll be looking at electricity. This first one, we're really just looking at the real basic concepts, current, voltage and resistance. If you can really get a good grasp of what they are, it makes things a lot easier. But I find that people often don't understand the basics at the beginning and then things get a bit confusing. So really try and follow this, really get to grips with what these 3 things are: current, voltage and resistance. So I've said it already really. What we'll be looking at: what is electric current, what is potential difference or voltage. AQA seem to love to use the term potential difference. Everyone else seems to use voltage, but they are interchangeable for GCSE certainly. What is electrical resistance as well? So first of all, the idea, what is electricity? It's such a difficult concept to grasp. What is electricity? Well, all we know, what we understand, is that there are things that conduct electricity and there are things that don't conduct electricity. From your Key Stage 3, from Year 7, probably even from primary school, you might have looked at circuits and seen what materials conduct electricity, what materials allow current to flow. All metals are conductors. So if you put a circuit together and you have a metal in it, with the wires, obviously they're made of metal, they are going to allow that current, that electric current, to flow. We'll talk more detail about what current is in a second, but they're going to allow a current to flow. Whereas, move myself over there, insulators, bad conductors, they have very high resistance, a term we'll use later, and they do not allow current to flow. They resist the flow of electrons. So I think fairly straightforwardly, what would you expect to be a conductor? What would you expect not to be a conductor? Copper obviously is a conductor. It's a very good conductor of metal. Rubber, not. Steel is a metal, so yes. Mercury is a metal, even though it's a liquid. Paper, an insulator. Plastic, an insulator. Diamond, an insulator. Both forms of carbon, you'll know from your chemistry. Carbon and diamond and graphite, both forms of carbon, but graphite, interestingly, is a conductor, even though they're both non-metals, they're both carbon. So, electric current is the rate of flow of charge. But already we've got an issue. What is charge? Well, charge is a really basic concept, really fundamental to the universe. People ask me, what is charge? How do you get to the bottom of it? Well, it's difficult. It's a bit like asking, what is mass? Okay, we know that we have mass. We know that masses produce gravitational fields. In a similar way, we know that some things have charge, some things don't, and those charges are affected by electric fields. Just be aware that some things have charge and some things don't. And there are 2 types of charge. There are positive charges and there are negative charges. So again, from your chemistry, I'm sure you'll be aware that the atom consists of a nucleus, which is protons and neutrons. Protons positive, neutrons are neutral, and it's the electrons that's in the orbits or outside the nucleus that play a dominant role in electric current, especially when we're talking about metals. Okay, from chemistry, again, you might be aware of the fact that ions can carry charge. So ions can carry a current as well. But almost always we're going to be talking about electrons. So these electrons outside the nucleus of the atom, these are the things that are most likely to be carrying the charge that produces this electric current. This flow of charge is electric current. Sometimes we talk about relative charge. Again, in chemistry particularly, we talk about relative charge of being a proton has a relative charge of 1, or we might talk about an electron having a relative charge of -1. But what we talk about in physics is charge as being a unit of Coulomb. Okay, Coulomb is a very large amount of charge. Okay, so now we know hopefully what provides the current, what produces the current. We need to look into current in a little bit more detail. So here's your definition that you need to know. Electric current is the rate of flow of electric charge. And an electric current of 1 ampere, which is what current is measured in, flows when the charge of 1 Coulomb passes a point in an electric circuit every second. So if 1 Coulomb of charge, it's a lot of charge, it's lots and lots of electrons. If they pass every second, you've got 1 ampere of current. So all metallic conductors that we talked about, they are carrying the electrons. They're carrying that negative charge from the one side, the negative side of the power supply, around the circuit to the positive. So you can just imagine this battery, which is transferring energy from one end here. These electrons are going to be flowing around in this direction, away from the negative end towards the bulb, where they're going to transfer energy, and we'll talk about how that works shortly. But all we're talking about is this flow of electrons going through the metal, through the battery where they gain energy, and through the bulb where they transfer energy. Yeah, I've said it before, but I'll remind you, electrons carry a tiny, tiny charge. So a coulomb is trillions and trillions, literally trillions and trillions of electrons. So when we're talking about 1 coulomb, we're talking about loads and loads and loads of electrons. So this is a PhET demonstration. Free, you can download this or just open it on a browser very, very easily. Really worth playing around with. There's lots of things you can do on it. But it's one of the things that I want to show you is just a really good demonstration of what current is. So what we've got here, we've got the battery here. The battery's got a voltage, which we'll talk about shortly. But it's providing energy to these charges, these coulombs. I'm going to suggest that each of these little negative balls is a coulomb, and that those coulombs are moving around. Okay, they're moving at a certain rate. Okay, and I'm putting an ammeter here. I'm going to put an ammeter in series. An ammeter is the device that measures the current. I need to put it in series, again, another term we'll talk about, but hopefully you know what that means, so that the current is flowing through that ammeter. And you can see that the current is 0.9 amps at the moment. If I increase this voltage, which is the amount of energy I'm giving to each of those coulombs, it's effectively giving it a greater push. And because I'm giving it a greater push, you can see these coulombs are moving faster. And as a result, the current is increasing. Okay, so that 2.3 amps literally means that every second, 2.3 coulombs of charge are passing through that current. And you'll know, hopefully, that anywhere in a series circuit, that current is going to be the same. So if I take an ammeter, this isn't how an ammeter would be, but I can use this little probe. An ammeter actually has to be put in part of the circuit. But if I just move this probe around, you can see that wherever I am within this series circuit, it's the same current. Just like a river, that flow should be constant unless you have a resistor that's going to change it. So there's two ways I can change the current. I can either increase the resistance of this, again, terms we'll talk about in more detail, but I can increase the resistance of this lamp. Yeah, I'm literally impeding, I'm slowing down the current, trying to resist it like a dam might try and resist a river, or I can increase the voltage or decrease the voltage, which effectively is changing the push. Okay, I'm trying to push those coulombs around the circuit. So if electric current is the rate of flow of charge, of course we can put together a nice formula. This is the formula that you're going to actually get given. I like to think of current, because the definition is the rate of flow of charge, I like to think of current as the charge, Q, in coulombs, divided by the time. So that would be in coulombs. That would be in seconds, of course. And of course, you will need to change your time into seconds. You need to change your current into amps. And you need to change your charge into coulombs. Otherwise, this formula is not going to work. In particular, the time. Often you'll get, again, minutes, hours, days. You need to convert that into seconds or it's not going to work. That's how I like to think about it. Unfortunately, your exam boards think otherwise, and they will give you that formula. Q equals IT. In other words, charge equals, in fact, it's up here, current times time. So there are just one more thing to think about with current, which we'll talk about in another video as well. Lots of things to think about in other videos, but this is just an overview, yeah? So direct current is when you have the current going in one direction. Not a great animation, this, but you can see that if we had a battery here, a battery is sending a current around the circuit in one direction. Whereas if you have alternating current, then what you're going to have when you close that switch is the current going one direction, and then it's going in the other direction. Then it's going one direction, then it's going the other direction. Okay, uses of that and why we need that we'll talk about in further videos. But referring to that original equation, let's have a go at this. Calculate the charge passing through a device when a current of 500 milliamps flows for 3 minutes. So already I've thrown a few slightly tricky parts in here. The formula we're going to use is the one that I just showed you. Q equals IT. This is our charge, this is our current, and this is our time. You can have a go at that, pause the video if you like, but I'm going to go straight onto the answer. The thing to remember is that your current here is in milliamps, so that needs to be converted into amps, and your time here in 3 minutes needs to be converted into seconds. So there's your formula. That's the information you've got converted into your amps and your seconds, and your charge should be 90 coulombs. Have another go. Pause it if you want. Actually slightly easier, but you need to rearrange this. With 3 amps for that one. And then if you want a few more, just to get some practice in, here's some you-dos. Pause the video, have a go at those. I'll give you the answers in a second. So here's your answers. Okay, so that is current, electric current, the flow, the rate of flow of charge. The next thing to talk about is voltage, which again I've touched on. It's very hard not to talk about the other things whilst I'm talking about what's going on. But voltage, what you're probably taught at Key Stage 3 is that it is this push, it's this driving force. I don't personally like it. It's a useful way of thinking about it. It's the push of those coulombs, those electrons around a circuit. But more importantly, and what your GCSE, your exam boards want to know, is that it is how much energy is transferred to a circuit. So what a battery does, if we think about a battery is transferring energy. Hopefully you know that a battery contains chemical energy, and it's going to transfer that chemical energy into whatever you're trying to do in your circuit. If you've got a lamp in your circuit, you're trying to transfer that chemical energy into thermal and light energy in the lamp. How does it get there? What's the transfer? The transfer, again, we should know that, is an electrical transfer, electrical current. So the voltage is how much energy is being given by that battery. So the voltage or potential difference of a battery is equal to the energy in joules provided to each coulomb. So those coulombs that we looked at going around the circuit, they are each given a certain amount of energy. And if they're given if each of those coulombs are given 1 joule, then there is a potential difference or a voltage of 1 volt. So in your formula booklets, again, slightly confusing possibly. I like to think of it as voltage as how much energy per coulomb, energy for given charge, but your booklets would like you to know this. Just a rearrangement of it. E equals QV. The energy equals the charge in coulombs multiplied by the voltage in volts. So back to my FET here. Let's see how we can relate this to voltage. This time I'm going to use a voltmeter. Voltmeters, as you hopefully know, but we will talk about in a future video, need to be placed across devices in parallel. So you can't just have one point and say what's the voltage at that point. The reason why AQA calls it a potential difference is because it is a difference, importantly. Okay, there was a difference in energy between this point and this point. So if I put one probe here, these electrons or these coulombs of charge have no energy. Okay, although they're moving, they don't have any electrical energy. But this battery is transferring energy from chemical and it's transferring via electricals, so that by the time those coulombs get through to the other side, these particular coulombs, each of these blue little balls, each of these coulombs have 22 joules. Each coulomb has 22 joules. So the voltage or the potential difference between this point and this point is 22 volts. Now, you're only going to gain energy if you put it through a cell, if you go through a cell. Or you might lose energy if you go through a device. So again, here, if I think about this lamp is transferring energy from electrical energy into light and heat. So again, if I think about the energy here, well, these coulombs each had 22 joules of energy. They've gone through the device, the lamp in this case, and they're going to leave with no energy. So again, what is the difference? Well, the difference is going to be 22 minus 0. They start with 22, they end with 0, so the difference is 22 volts. In other words, each of those coulombs have transferred 22 joules of energy into light, which is why it's going bright. But what about this? If I put my voltmeter across this point and this point, what do you think is going to happen? Well, these coulombs have 22 joules. They haven't gone through a device. They're not losing any energy. So these ones here still have 22 joules. So if I put my voltmeter across these 2 points, there should be no difference at all. They haven't transferred any energy. So there is no potential difference. There is no change in energy between coulombs at this point and coulombs at this point. I'm going to put it back across the battery for a second. And if I increase my voltage, my battery, I can see that my lamp is getting brighter. My current is going greater because I'm pushing. It's another way of thinking about voltage, is the push through. But I'm pushing those coulombs through a bit more forcefully. But I'm also providing more energy to each of these coulombs. So if I'm providing more energy for each of these coulombs, more energy is also available to transfer to the lamp. And so as I increase the voltage, my lamp is also going to transfer more energy. Therefore, it's going to be brighter, more light energy. So that is the idea of what voltage actually is. But of course, we need to be able to apply that formula. So again, here's the formula we have. E equals Q times V. Calculate the voltage of a battery if it supplies 300 joules of energy to 50 coulombs of charge. And you're just going to plug that into the formula, rearrange it, and you get your 6 volts. So here's another way of looking at this. It's similar to the FET that I wanted to show you. Here's the battery. The battery is providing energy per coulomb. So these little trucks here are your coulombs, but they've got no energy. They go through the battery, they're gaining this energy. They're going through this ammeter, so it's got a current, which is going to be in coulombs per second. So that's telling you how fast they're going through. And then this lamp is using this energy, this coal, if you like. So it's giving out that energy, it's transferring the energy, in this case, as light. But if I increase the voltage, what I'm going to also do is start those coulombs to move faster. So the current's going to increase. Now I'm providing more energy per second. Okay, not only are there more joules per coulomb, it's also going faster, so this lamp is going to be brighter. So if we increase the voltage, we're giving the charges more energy and their rate of flowing will increase. Note, it's a small point, but it's important if you go on to A-level, the battery is not giving the charges kinetic energy. Even though they look like they're moving faster, it's the flow. It's a complicated point, but it's the flow that is increasing, not the fact that they are moving around faster. Okay, but the current will increase. The voltage increases, the current will increase. If we kept that voltage, now we've slowed it down. Well, how have we slowed it down? Well, an idea we're about to introduce is this idea of resistance. So I've increased the resistance. Rather than putting a lamp in here now, I've put a resistor. And what a resistor does is try and reduce the current. So even though this voltage is as high as it was before, this resistance is trying to reduce that flow. As I said before, it's like a river flowing freely, and then it comes to a dam. The resistor is like the dam. It's trying to impede that current, trying to impede the flow. So we increase the resistance in the circuit, it will reduce the flow of charge. But it will not affect the voltage. Okay, the voltage is set by what we set it at with the battery or the power pack. Okay, so have a go at these questions. Remember, our formula is E equals QV. See how you do with that. Okay, here are your answers. And just to test your understanding a little bit, I can't make myself any smaller there, but hopefully you can see that. Electric current, I'll just have a go at this and I will answer the questions in a second. Okay, the answers: electric current is the rate of flow of electric charge. Electric charge is measured in coulombs. A battery provides electrical energy. The amount of energy provided per coulomb of electric charge passing is equal to the voltage or potential difference of the battery. The main supply gives 230 joules every coulomb. Something I hadn't mentioned actually, the main supply in your homes gives 230 to 240 volts, which means it's providing 230 joules to every coulomb of charge. So finally, resistance. Here's your definition. Resistance is the opposition that an electrical device has to the flow of electrical current. All devices, whatever they are, have some resistance. Some devices have less resistance. Even a wire has some resistance. And you're trying to, in a case of a wire, trying to reduce that resistance, because resistance also means that it's going to lose energy. Resistance is measured in ohms, that funny Greek letter. You might see various forms of it, but I tend to draw it like that. Okay, that's it in printed form. That's what the resistor looks like. I'm sure you've seen them in school, and that's the circuit diagram for a resistor. So the resistance equation, not quite the same as Ohm's law, which many of you will think it is the same thing. Here is the formula for resistance. You can determine the resistance if you know the voltage and the current. Resistance is voltage divided by current. Voltage in volts, current in amperes, and resistance in ohms, as hopefully you know. This is the formula you'll get given, V equals IR. And as I said, it's not quite the same as Ohm's law. In the next couple of videos, we'll be talking about Ohm's law and why, and we'll be using this formula a lot, but I will mention why it's not quite the same as Ohm's law. This formula is always true, whereas Ohm's law is a specific example. We'll look at this in more detail next video as well, but how do we measure the resistance of devices? Well, this is a circuit diagram that you have to be completely familiar with. The number of exam questions that come up with this diagram is quite phenomenal. So what you're always going to be doing, and I will mention it again in the next video, the device that you're trying to measure the resistance of is going to be in series with your voltage provider, whether that's a power pack or a battery. That's actually going to be variable normally. Again, we'll talk about it in more detail in the next video. But you want to make that a variable voltage, so it usually has a little variable resistor in there. This voltmeter has to be in parallel across the device, this lamp, and your ammeter has to be in series. This diagram is often like 4 marks. As I say, we'll look at it again in the next session and look at it in more detail. So using that formula, I just want to practice using the V equals IR. Here are some examples. Calculate the resistance. Here's the formula again. Let me write it up for you. V equals IR. Calculate the resistance of a lamp if a voltage of 4 volts causes a current of 3 amps to flow through the lamp. Answer the question, and here is the answer. There's your formula. There's the calculation. And there is your answer. Notice what I've been doing in all of these calculations is to substitute. I've talked about that before. Substitute into the formula you're given. Rather than rearranging it, substitute first a mark. Rather than rearranging it, rearrange it second a mark. You don't get a mark for just rearranging. So substitute first. Question 2, have a go at this one. Slightly harder, not much harder. And the answer, there's your formula again. Subbing in, again, notice I've substituted these values into V equals IR, then I've rearranged it. There's your answer. Last one here. What is the current running through the redstone in milliamps? Notice they want it in milliamps. So I'm just moving that. There you are. 500 ohms, voltage of 40 volts. What is the current in milliamps? And your answer, V equals IR. This time I've rearranged it. I probably should have substituted it first if I wanted to maximize my marks. As long as I'm getting the answer correct, I'll be fine. But if I want to make sure that I'm getting marks, even if I get my final answer incorrect, I want to substitute first. So I would suggest what I should have done would be to say my voltage is 40, my current is what I want, and my R is 500 ohms, and then rearrange to this form. A few more practice questions to have a go at. And here's your answers. Okay, what we should know. We've defined electric current. We've used the formula Q equals IT, and we've done some calculations. We've defined voltage and potential difference and explained how it drives the current around the circuit. We've used E equals QV to define voltage, and we've also defined electrical resistance. And we've used V equals IR. So we've covered a lot of ground there. We'll look at a lot of these ideas again, but just to get an overview of how current, voltage and resistance all work together, I think is really important. So I hope you found that useful. Do check out my Facebook, or if you need some help, get in touch, tobytutorsphysics.com. All right, great, see you soon, bye.